You ever look at a really complex program and just wonder, how in the world do they write code that's so smart and efficient? Well, today we're going to pull back the curtain on two of the biggest secrets that make it all happen: generalization and encapsulation. Okay, so let's start with a puzzle. Imagine you've got this one tiny little piece of code. It does one job, and that's it. How do you take that single, simple instruction and somehow turn it into a machine that can automatically build this entire multiplication table? I know, it looks like a huge jump, but trust me, the logic behind it is actually pretty straightforward. We're going to build this thing together, one piece at a time. It's a great way to code called incremental development. You just take small, easy steps to create something really impressive. So, let's get started. Every big build starts small, right? So our first goal is super focused. We're not worrying about the whole table yet. We're just going to figure out how to create one single row. Let's start with the multiples of 2. All right, here's our first chunk of code. It's pretty basic, really. It's just a simple loop that takes the numbers 1 through 6 and multiplies them by 2. And the output? Yep, you see it right there. It prints the 2 times table, exactly what we wanted. Our first brick is officially in place. But, and this is a big but, there's a problem. This code is what you'd call a one-trick pony. We built it to do one thing and one thing only: print out the multiples of 2. There's zero flexibility here. So here's the real question. What happens when your boss comes along and says, great, now I need the 3 times table or the 4 times table? Are we supposed to just copy and paste this code over and over again for every number? No way. That's not smart, it's not efficient, and it's a fast track to messy, unreadable spaghetti code. And that brings us to our first huge concept: generalization. Think of it like this. Our first piece of code was like a wrench that only fits one single bolt. Generalization is all about turning that into an adjustable wrench, a single tool that can handle all sorts of different jobs. And here's that upgrade in action. We've turned our code into a smarter function called print_multiples that takes an input, which we're calling n. Now we can just tell it which row we want. You need the 3 times table? Just call print_multiples 3. The 4 times table? Print_multiples 4. See? Just like that, our one-trick pony is now a flexible workhorse. Okay, this is a massive improvement. But, solving one problem often reveals another one. To build the whole table, we still have to sit here and manually call that function for every single row. It's better, for sure, but it's still, well, it's tedious. So, what we really need now is some automation. We've got our adjustable wrench, our flexible tool. Now let's build an assembly line that can run that tool for us, again and again, until the entire job is done without us lifting a finger. And this leads us to our second powerhouse principle: encapsulation. If generalization gave us the tool, encapsulation is about building the factory that uses the tool. We're just wrapping up all those repetitive steps into one automated package. You push one button, and the whole assembly line just goes. And check this out. This is the payoff. Our assembly line is just another simple loop. All it does is call our print multiples function for every number from 1 to 6. And just like that, boom, the whole multiplication table is built automatically. This is awesome. Our factory is up and running. It's producing exactly what we want. But when it comes to writing really good code, there's always a way to make things even cleaner, even more organized. Right now, that assembly line, the loop, is kind of just sitting out in the open in our code. The next level of professional coding is to encapsulate the entire assembly line itself into its own neat, tidy, self-contained unit. Just look at the difference here. On the left, you've got all that logic cluttering up the main part of our program, but on the right, we've tucked that whole assembly line away inside a new function called print tables. Now, our main program is just one simple, clean, easy-to-read command. So much better. We are so close now. Our code is automated, it's organized, but look closely. There's still one little limitation baked in. See that number 6? It's hard-coded right into our program. So what happens if we suddenly need a 10 by 10 table or a 20 by 20? And this is the grand finale, where we put everything we've learned together. We already did step 1, right? We encapsulated the loop. Now, for the final masterstroke, we're going to apply our first principle, generalization, to our new encapsulated factory. And there it is, the final perfect version. We've basically added a size dial to our print_tables function, an input we're calling high. Now we can tell our factory exactly how big we want the table. Print underscore tables of 6 gets you a 6 by 6. Print underscore tables of 12 would get you a 12 by 12. It's fully automated, totally flexible, and just beautifully organized. So, why does all this matter? What's the big takeaway? It's simple. Generalization gives your code flexibility, the power to adapt. Encapsulation gives it organization. It hides all the messy details and makes your code easy to manage. And when you use them together, that's when you start writing clean, powerful, reusable code that will save you tons of headaches down the road. Think about it. We started with one line of output, and by applying these two simple principles step by step, we built a powerful and adaptable code factory. We're diving into one of the most fundamental building blocks in all of programming, the array. You ready? Let's get into it. Okay, so let's kick things off with something you're probably already familiar with. We've all used simple variables, right? And you can think of them like a single box. They're designed to hold just one thing at a time. So, take a look at this line of code. The variable mult can hold just one result. Maybe it's the number 10, maybe it's 20, but that's it. One box, one value, simple. But that brings up a really big question, doesn't it? What happens when you need to handle more than just one value? What if you need to store, a whole list of high scores for a game? Or the temperature for every day of the week? And that right there is the huge difference. A single variable is like a coffee cup. It holds one thing. An array, which we're about to get into, is more like an egg carton. It's one container, sure, but it's designed to hold a bunch of individual items all together. And that's where our solution comes in. Let's talk about the array. This is a super powerful tool that C gives us to manage big collections of data and do it really efficiently. So what is an array exactly? Well, at its core, it's just a container. It's a container that holds a fixed number of values. And here's the really important rule. All of those values have to be the exact same data type. They all have to be integers, or they all have to be characters. No mixing and matching. So what does that actually mean for us? Well, a couple of things. First, like I said, you can't put an integer and a character in the same array. And second, the size is locked in. Why? Well, it's because C needs to know exactly how much memory to set aside for this thing right from the get-go. And by the way, each individual item that we store inside this container, we call that an element. Okay, so we've got this container, and it's full of these things we're calling elements. But how in the world do you grab just one of them? Well, the answer is in how the array is structured. Think of it like this. Every single element has its own unique address, kind of like a house number on a street. And in the world of arrays, we call that address its numerical index. And here we go. This is probably the single most important and sometimes the most confusing thing you have to remember about arrays in C. The numbering, the index, it doesn't start at 1. It always starts at 0. So if you want the first thing in the array, you don't ask for number 1. Nope. You ask for index 0. If you want the second thing, you ask for index 1. The third thing is at index 2, and on it goes. This whole concept is called zero-based indexing, and it's a huge deal in C and a ton of other programming languages. All right, enough with the theory, right? Let's see what this actually looks like when you're writing code. How do you tell C, hey, I want to build one of these awesome containers? Boom, there it is. That one little line of code is a complete array declaration. I know, it might not look like much, but it's packed with information for the computer. Let's pull it apart piece by piece. First up, we've got the data type. See that int? That's us telling the computer, hey, this container we're building, it's only going to hold integers. Next, we give it a name. In this case, first array. Pretty straightforward. That's just what we'll call it whenever we need to use it. And then, and this is super important for the declaration, you see those square brackets with the number 7 inside? That's the size. We're telling the computer, hey, I need you to set aside enough space for exactly 7 integer elements. And yeah, you can't skip this step in C. It's not optional. You have to specify the size right when you declare the array. That's what lets the computer block out that perfect fixed chunk of memory for you right from the start. And just like that, you know the what, the why, and the how of creating arrays. So let's do a quick recap to make sure all of this new knowledge really sticks. So what are the big takeaways here? First, remember, variables hold one thing. Arrays hold a whole bunch of things. Second, those arrays have a locked-in size and can only hold one type of data. And the really big one, C starts counting from 0, always.
And finally, to make one, all you need are those 3 ingredients: the type, the name, and the size. That's the whole recipe.
So you know how to build the container. You've built the shelf. The big question now is, how do we actually fill it? How do we put our stuff inside it? And that, my friends, is where things start to get really powerful. The array. You know, if you've ever wondered how a computer can possibly keep track of tons of data, like all the scores in a video game or a huge list of names, well, arrays are the simple and super powerful answer. So let's just start with a problem. Imagine you're coding a game and you need to save the top 100 high scores. What are you going to do? Create 100 different variables, score 1, score 2, score 3, all the way to 100? No way. That would be a complete nightmare to manage. Luckily, there is a much better way to do it. And that better way is, you guessed it, the array. The best way to think about it is like a filing cabinet for your computer's data. Instead of having papers scattered all over your desk, an array gives you one single, organized spot to put a whole bunch of similar things. Okay, so what does that actually mean? Well, there are 2 really important parts here. First, everything you put in an array has to be the same type. So you can have an array of numbers or an array of letters, but you can't just mix and match. And second, they're stored in a contiguous block of memory. That's just a fancy way of saying they're all lined up, one right after the other, which makes it incredibly fast for the computer to find what it's looking for. Now, in a language like C, creating an array is actually pretty simple. It can look just like this: int myArray5. That single line of code is basically you telling the computer, hey, go find a block of memory that's big enough to hold 5 integers, and from now on, I'm just going to call it myArray. And this is what that looks like inside the computer. It's set aside those 5 empty slots, just for us. But check out the numbers on the left. Each one of those slots gets its own unique address, a number that we call an index. And that index is the secret to everything. Okay, so we've got our filing cabinet, we've got our empty folders, but they're not much use if we can't actually put stuff in them or take stuff out. This is where that index really starts to shine. An index is really just the address for a specific box in our row of boxes. It's the label on the folder that lets us go straight to the one we want without having to rummage through all the others first. And here's how you actually use it in the code. See those square brackets? You just pop the index number in there, and you can aim for a specific slot. So here, we're putting the number 10 into the slot at index 0, 20 goes into index 1, 30 into index 2, and you get the idea. It's a super direct, super efficient way to handle our data. Okay, now this is where arrays go from being useful to being incredibly powerful. We don't have to just type in a number like 0 or 1 for the index. We can use a variable instead. This simple little trick lets us write code that can just loop through every single element in a giant array automatically. It's the foundation for so much of what makes programming work. All right, let's pause here because we've come to the single most important rule you have to remember when you're working with arrays, not just in C, but in most programming languages. It's a classic stumbling block for beginners, but once you get it, you'll never forget it. This quote right here just nails it. If you make an array with 5 items, you might think the indexes go from 1 to 5, right? Nope. They go from 0 to 4. That last item is always at an index that's 1 less than the total size. It feels a little weird at first, but it's all about how computers count things. And this chart shows the difference perfectly. We as humans, we start counting things with the number 1. But for a computer, the index is more like an offset. It's asking, how many steps do I need to take from the very beginning? Well, for the first item, you don't have to take any steps at all. You're already there. So that's 0 steps away. So if there's one thing you take away today, let it be this. The first element in any C array is always at index 0. Just burn that into your brain. It will save you from so many headaches later on, I promise. So a single list of items is great, super useful. But what happens when your data is more complicated from that? What if you need to represent something like a grid? A spreadsheet, a chessboard, or even the pixels that make up your screen. This is where multidimensional arrays come into play. By adding that second set of square brackets, we're not just creating a single row of boxes anymore. What we're really creating is an array of arrays. And that is the perfect way to build a grid or a table.
And you can see right here what that little int myArray22 line of code created. It's a table. It has 2 rows, and remember, they're indexed 0 and 1, and it has 2 columns, also indexed 0 and 1. It's just the perfect structure for any kind of data that fits in a grid.
And getting to a specific cell in that grid is just as easy. You just have to give its coordinates, kind of like on a map. You give the row index first, then the column index. So if you look at the example, my array from 1, 0 takes us to row 1, column 0, and there's our number 3. Simple as that.
All right, so let's just quickly recap the big ideas here. Arrays are your go-to tool for organizing big groups of data. Just remember, all the items have to be the same type, you find them using an index, and that index always starts at 0. And if you need to, you can even build grids with them. It's how you go from having 100 separate things to one neat, organized collection.
You know, getting a handle on arrays is a huge step. They really are the backbone of so many other, more advanced ways of structuring data. But notice, their real strength is in ordered lists. And that brings up a really interesting question. What if your data doesn't have any particular order? How do you deal with that?
Strings. I mean, it seems simple enough. It's just text, right? But in a low-level language like C, there's this really elegant and powerful system working just under the surface. So let's dive in. We're going to kick things off with a little puzzle that perfectly shows you how C thinks about text. On the surface, it's a super simple question, but the answer reveals the entire philosophy behind how C handles data. So what is the difference here? I mean, to you and me, they look basically identical, right? The only thing separating them is a pair of double quotes. But to the C compiler, these two things are from completely different universes. One is just a label, and the other is the actual stuff. Let's dig into what that really means. Okay, check this out. On the left, hello without any quotes is just a variable name. It's a placeholder, a container. We could use that name to hold the number 1 or, I don't know, a memory address, whatever. But on the right, hello with the quotes is the thing. It is the data. It's the actual sequence of characters we want to do something with. So this chunk of text data, the one all wrapped up in quotes, it has a formal name in C. And just understanding what the compiler calls it is really the first big step to unlocking how it all works. And its official name is a string. Simple enough. So from this point on, whenever you see text inside double quotes, you know you're looking at a C string. But okay, that just gives it a name. What's actually happening inside the computer's memory? And this right here is where C's low-level power really starts to shine. See, unlike a lot of modern languages that have a special string type built in, C builds the whole idea of a string from a much more basic building block. Let's pull back the curtain. And there it is, the big reveal. A string in C is not some special magical thing. It is, quite simply, an array of characters. It's a sequence, a collection of individual characters, all stored one after another, lined up in a row in memory. This picture illustrates it perfectly. The computer doesn't see the word hello, it just sees 5 separate character values. H, then E, then L, L, and O, all lined up. But wait a minute. This brings up a really important question. If it's just a sequence of characters, how does the computer know when to stop reading? What's to stop it from just reading past the O into whatever random junk is next in memory? To know where to stop, any function that works with strings, think pointf or something like that, it needs a really clear signal. And C has a brilliant solution for this. A special, invisible character that gets automatically tacked on to the end of every single string you create. This is the secret ingredient. It's called the null character, and you write it as /0. This one single character acts like a universal stop sign for strings. It is C's incredibly simple and efficient way of marking the end of a string without having to waste extra memory storing its length somewhere else. You know, this analogy just nails it. The null character doesn't change the content of the string at all. It's not part of the word hello, but it provides that essential punctuation that the computer absolutely depends on to know where the string's data actually ends. So, here's the crucial takeaway from all this. The string hello has 5 letters that you can see, but it actually takes up the space of 6 characters in memory. 5 for the text and 1 extra for that invisible null terminator that marks the end. Okay, so we've kind of cracked the case, right? We know that a string is really just a null terminated character array. So how do we actually create one and store it in our code? Let's take a look at the common ways to do it. So the most manual way, the long way, is to declare a character array of the exact size you need, 6 in this case, and then assign each character one by one. The key thing here is that you are responsible for manually putting that null terminator at the end. And yeah, using the number 0 works just the same as /0.
A much cleaner way to do it is to use an array initializer. This lets you define all the characters on a single line. It's way more concise, and you're less likely to make a mistake. But notice, you still have to remember to add that final null terminator yourself. And finally, we get to the easiest, safest, and, let's be honest, by far the most common method, the string literal. When you use the double quotes, you're basically telling the compiler, hey, you handle this. It automatically counts the characters, it allocates the right amount of space, and, most importantly, it automatically adds that crucial null terminator for you. So much easier. So let's just boil this all down. At its heart, a C string isn't some complex, fancy data type. It's just an array of characters. And the entire system, the whole shebang, hinges on one simple rule. That array has to end with the null terminator, /0, which acts as that universal stop sign. It's a simple idea, but it's incredibly powerful. So now you know how to properly create strings in C. You get it. But what about actually working with them? How do you safely copy one string to another, or stick two strings together, or even just find out how long one is? Well, that's where things get really interesting. You know, there are some things in programming that just trip everyone up at first. And in C, string initialization is a big one. So today, we're going to demystify why your perfectly logical-looking string code keeps failing. Trust me, if you've ever been stumped by this, you are not alone. All right, let's kick things off with a little puzzle. We're about to look at a snippet of C code that seems like it should be the simplest thing in the world. But, spoiler alert, it won't even compile. And figuring out why is the key to unlocking a really fundamental concept in C. You see, when this code fails, it's not some random bug or a typo. It's actually the compiler enforcing a really strict, non-negotiable rule about how C deals with arrays and memory. And once you get this rule, a whole class of potential bugs just vanishes. Okay, so let's break this down with our first case. This is probably the most common mistake people make right out of the gate when they're trying to set up a new string. So here's the code. Looks simple enough, right? We're declaring a character array, we're calling it greeting, and then on the very next line, we're trying to put the word hello into it. It reads just like English. But the C compiler will take one look at this and say, absolutely not. So what do you think? Why is this such a problem? Take a really close look at that first line, char greeting shell. The whole reason for the failure is hiding in plain sight, right there. It's about what's missing. And here it is. When you declare an array in C, the compiler needs to know right then and there how much memory to set aside for it. By leaving those square brackets empty, you've basically said, hey, I need a box for some stuff, without ever saying how big the box should be. The declaration is incomplete, so the whole program build just fails. And what's really interesting here is where it fails. The error is on that very first line. That second line, the greeting equals hello part, the compiler never even gets to it. It hits that incomplete array declaration and just stops dead in its tracks. Okay, so you're a smart developer. You see the problem. Aha, you think. The compiler needs a size. So you fix it. But in doing that, you walk straight into another, much sneakier trap. So, the logical fix seems pretty obvious, right? The word hello is 5 characters, and in C, we always need one extra spot for that invisible null character that signals the end of the string. So, a size of 6 should be perfect. And here's our updated code. We've declared greeting to, we've given it exactly the right amount of space, 6 characters, and then we try to assign hello to it. Okay, this has got to work now, right? And nope, it fails again. And this is the part that drives so many people nuts. The size is fixed, the logic seems totally sound, but we've just slammed into an even deeper rule about how arrays work in C after they've been created. And this slide right here is the golden rule. That equal sign for arrays, it's a one-time only deal. It's a special operator that only works for initialization, meaning during the declaration. You are just not allowed to use it for assignment after the fact. So why is this forbidden? Well, think of it this way. The name greeting to isn't really a variable. It's more like a constant, a permanent address marker for the start of a block of memory. The string hello is also a pointer to another block of memory somewhere else. You simply can't tell an array name to just abandon its memory and point somewhere new. It's fixed. Okay, so let's step back and put the pieces together from our two failed attempts. Because when you look at them side by side, they reveal the unshakable rules of string initialization in C that you just have to know. So here are the big takeaways. Number one, a character array needs a size. Period. The only, and I mean only, exception is if you initialize it on the exact same line, because then the compiler will do the counting for you. And number two, that equals sign is off limits for assigning to an array after it's been born. And this rule holds true whether you're using the double quote string syntax or the curly brace character list syntax. So now that you've seen what doesn't work, which, let's be honest, is more than half the battle, what's the right way to do it? Well, you've got two main options. Either you initialize the string on the very same line you declare it, or you use a special function like strcpy to copy the data into the array after it's been created. Mastering those two techniques is really the key to handling C strings like a pro.
Today, we're going to master how to do exactly that with strings in the C programming language. It might sound a little intimidating, but trust me, once you see the core idea, it's surprisingly simple.
But let's just start with a really basic question. When you see text change on your screen, maybe your score in a game or a word in a document you're editing, how does a program actually do that? How does it reach in there and swap out the letters? That's the puzzle we're going to solve right now.
Okay, let's dive right in. The whole secret to manipulating strings in C boils down to one single, powerful idea. Once you get this, I promise everything else just clicks into place. And that idea? It's simple. Strings are just arrays. So what does that even mean, a C-style string? Well, formally, it's defined as an array of characters. That's really it. So just for a second, forget any other complex ideas you might have about strings. Just think of it like this. It's a collection of characters, and each one is sitting in its own little slot. This is the key to everything.
In fact, a quote from our source material really just gets straight to the point. It says, strings can be manipulated like other arrays. This isn't just a friendly tip. It's the fundamental rule for everything we're about to do. If you know how to work with arrays, you already
So, if you're just getting your feet wet with C, I bet you've slammed right into a wall when it comes to strings. It can be so frustrating, right? But hey, don't worry. In this explainer, we're going to pull back the curtain and give you the first 3 essential tools you absolutely need to get a handle on strings. Okay, let's just dive right into the deep end. This error, this is basically a rite of passage for every new C programmer. You set up a string, you try to give it a new value later on, and nope, the compiler just yells at you. It looks like it should work, so what is going on here?
Okay, let's put these side by side. Look at the left with the integer. Super easy. Think of num as a little box. You can pop the number 10 out and put a new number in anytime you want. But on the right, with the string, it's different. str isn't really the box. It's more like a permanent label pointing to the start of a whole row of boxes in memory. You can change what's inside those boxes, sure, but you can't just peel that label off and stick it onto a completely different row. And that's the fundamental problem.
So, if the good old equals sign is off limits, what are we supposed to do? Well, this is when we call in the specialists. C gives us a dedicated toolkit designed for these exact situations. It's called the C string library. And this toolkit, string.h, is basically a collection of pre-built functions for handling what C technically calls null-terminated character arrays. I know that's a mouthful, but it's just a fancy way of saying it's an array of characters that has a special, invisible character at the very end, the null character, to signal, hey, the string stops here. And you know what's great? Unlocking this entire toolkit is incredibly simple. All you have to do is just add this one line to the top of your C file, #include string.h. That's it. You do that, and you've got access to all the powerful tools we're about to talk about. All right, tool number 1, let's grab it. This one is going to solve that first problem we had right at the beginning. We can call it the copier, but its official name is strcpy. So strcpy, it's short for string copy. And it does exactly what you'd think. It takes all the characters from one string, the source, and carefully copies them, one by one, into the memory space of another string, the destination. This is the official, C-approved way to do what we thought the equal sign would do. The syntax is pretty straightforward. The first thing you give it is the destination. That's where you want the new string to end up. The second is the source, the string you're copying from. Just burn this into your memory. It's always destination, then source. And look at this. This shows the whole journey. We start with an array, str, ready to hold our string. Then in step 2, we try the old way, str equals hello, and we get that error. But then step 3, we bring in our new tool, strcpy, and it works. Just like that. Our str array is now filled with the characters for hello and that all-important null character at the end. Problem solved. Awesome. So now we can assign strings. But what if you want to join 2 strings together, like hello and world? For that, we need our second tool from the kit, the linker, also known as stccat. Stratcat stands for string concatenate. You know, concatenate is just a fancy programmer word for linking or chaining things together. This function takes a source string and tacks it right onto the end of the destination string. Now, the syntax looks exactly the same as strcpy, right? strcat, destination, source. But don't let that fool you. The result is totally different. It doesn't overwrite the destination. It adds to it. Okay, let's peek into the computer's memory for a second. Before we do anything, we've got 2 totally separate strings, str1 and str2. You can see each one has its characters, and, importantly, each one has its own null terminator, that 0, telling C where each string ends. Now we're going to call the function. We're telling C, hey, take whatever's in str2 and stick it on the end of str1. And here's the magic. Check it out. Stratcat is smart. It goes into str1, finds that null terminator, throws it away, and then starts copying str2 right into that spot. The result? str1 is now one long combined string, hello world, with a single new null terminator at the very end. And notice, str2 is still there, completely untouched. Okay, so we can copy, we can join. What's next? Well, a lot of the time you just need to know how long a string is. And for that, we have our third and final tool for today, the measurer, or strln.
String length is short for string length. Its job is super simple. You give it a string, and it counts up the characters one by one until it hits that null terminator, and then it tells you the final count. And the syntax is maybe the easiest one yet. You just call stringlen with the string you want to measure, and it hands you back a number, the length, which you can then save in a variable. So for a really simple example, if we ask stringlen to measure hello, it's going to count HELLO, and it's going to tell us correctly that the answer is 5. Seems obvious, right? But there is a huge gotcha here.
And this is absolutely critical. This is the detail that trips up everybody at first. Even though the string hello actually takes up 6 bytes of memory, 5 for the letters and 1 for the null terminator, stringlen only returns 5. It stops counting at the null character and does not include it. You have to remember this. Stringlen tells you the number of visible characters, not how much space the string takes up in memory.
Okay, that was a lot, but you now have 3 incredibly useful tools in your C programming toolkit. Let's do a super quick review of the main things to remember. First and foremost, you can't use the equals sign to assign a string after you've declared it, period. To get the tools that actually work, you have to #include string.h. From there, you use strcy to copy, strcat to join, and strlen to measure. And never, ever forget that strlen ignores that final null terminator in its count. So now you can handle the 3 most common string jobs out there. But this leads us to a really important and kind of dangerous question. When you use strcpy or strcat, you're copying bytes into a destination array. What happens if that source string is bigger than the destination array? What happens when you run out of space? Well, that's a story for another time, but it's the next critical piece of the puzzle.
Have you ever found yourself staring at a block of C code, just kind of wondering what's really going on in there? Well, today, we're going to pull back the curtain on a simple C program that plays around with strings. By the end of this, you'll see just how these basic functions are the real building blocks for pretty much everything else.
I mean, we've all been there, right? You look at a snippet, and you sort of get the general idea, but how the data actually moves from point A to point B, that can be a bit of a mystery. So let's treat this thing like a puzzle we're going to solve together, one piece at a time. And here are our puzzle pieces. We've got 3 character arrays, which is just the classic C way to handle strings, and 1 little integer variable. This is our starting line. Let's see what happens when we actually start running the code. Okay, so before we start messing with these strings, let's get properly introduced to our main characters here. You gotta know where they start to really appreciate their journey through the code. So here's the lineup. We have string 1, which is holding hello. Then there's str2 with world. And finally, str3, which is basically an empty box right now, just waiting for something to be put inside. Pretty straightforward. Now let's get things moving.
First up to the plate is strcpy. The easiest way to think about this one, it's like a photocopier, but for text. Its whole job is to make an exact duplicate.
Yep, just like the name says, strcpy is all about making a copy. It takes the contents of one string and just plops it right into another one, completely wiping out whatever was in the destination to begin with. So in our code, the first thing we do is call strcpy str3, str1. This is us telling the program, hey, take whatever is in str1 and make a copy of it inside str3. Let's see what that looks like. And voila! Just like that, str3, our once empty box, now holds hello. It's a perfect copy of what's in str1. Now here's a super important thing to know about strcopy. It's a bit reckless. It doesn't check if there's enough room. If str1 had been too big for str3, it would have just kept writing, causing a buffer overflow, which is a massive security problem. That's why a lot of programmers today use its safer cousin, strnocopy, which lets you tell it exactly how many characters to copy, max. All right, next up we have string concatenation. If strcpy was a photocopier, think of strcat as linking 2 train cars together to make one longer train. It's all about combining, not replacing. Yeah, concatenate is really just a fancy pants word for join together. So instead of overriding anything, stratcat just takes one string and tacks it onto the very end of another one. So our code calls strcat str1 str2. What does that mean? Well, we're about to take the world from str2 and stick it on the end of str1. And look at that. Our str1 variable has transformed from just hello into hello world. You'll notice there's no space in between. strcat doesn't add anything, it just smushes them right together. And you guessed it, just like its cousin strcpy, strcat can be dangerous. It also doesn't check for space, so you can easily cause another buffer overflow. The safer version here is strncat, which, again, lets you set a limit on how much you're adding.
Okay, our last function is stringlen, and honestly, it's the simplest one of the bunch. Just think of it as a tape measure for your strings.
The most important thing about strlen is that it doesn't change anything. It's totally hands-off. It just looks at the string, counts up the characters, and tells you how many there are.
So in our code, the last step is len equals string len of string 1. We're asking it to measure our new combined hello world string and then store that number in our len variable.
And the answer is 10. Makes sense, right? Hello is 5 characters, world is 5 characters, you put them together, you get 10. That number, 10, is now tucked away safely inside our len variable.
All right, let's zoom out for a second and look at the whole journey. We copied, we combined, and we measured. I think it's safe to say this puzzle is officially solved.
So let's just do a quick recap. First, strcpy did its photocopier thing and made str3 become hello. Then strcat came along and linked our 2 strings, turning str1 into hello world. And finally, strlen pulled out its tape measure and told us our new string was exactly 10 characters long. Each function had one specific job, and they all did it perfectly.
And there you have it, 3 of the most fundamental string functions in C, totally demystified. Okay, let's jump right into the puzzle. Take a look at this little piece of C code on the screen. It gets the length of an empty string, and then it tries to print the character at length -1. Now, this looks like it should work, but trust me, it will crash your program with a runtime error every single time. So the big question is, why? Let's figure this out together.
So before we can really dig into why our code is breaking, we need to have a solid idea of what correct string traversal looks like in C. Let's just do a quick review of the standard bug-free way to loop through a string. This is going to be our baseline for what write looks like.
Now, the technical term for what we're doing here is traversal. It's a fancy word, but it just means visiting each item in a collection one by one. And it doesn't matter if it's characters in a string or items in a list, traversal is one of the most fundamental patterns you'll find in all of programming. All right, let's break down this standard loop step by step. First, pretty simple, we start a counter, I at 0. Next, our while loop sets the rule. It's going to keep running as long as our counter I is less than the total length of the string. Inside that loop, we do the actual work. We print the character at the current spot. And finally, and this is the part that keeps the whole thing moving, we increment I to jump to the next character. It's a simple, clean process, and it works perfectly.
Okay, so now that we've seen the right way to do it, let's look at our first huge problem, the classic off by 1 error. This is, without a doubt, one of the most common and frustrating bugs you'll ever encounter, and it all boils down to a tiny but really critical misunderstanding.
So, let's say you just want to grab the very last letter of a string. A lot of people's first instinct is to get the string's length and then just use that length as the index. I mean, it makes sense, right? If the string is 11 characters long, then the last character must be at position 11. Seems logical.
So, I gotta ask you, if we run this exact code on the string hello world, what character do you think is actually going to pop up on the screen?
Well, surprise, you don't get the D you were probably expecting. Instead, you get, well, nothing. Or maybe some weird garbage symbol. And that's because you've actually accessed something that isn't really part of the visible string. You've found the invisible, null-terminating character, which is a secret marker C uses to know where a string ends in memory.
And this right here illustrates the core problem perfectly. C uses what's called zero-based indexing. So for a string like world, its length is 5. But the characters themselves are at indices 0, 1, 2, 3, and 4. The last actual letter, D, is at index 4. The length of the string, which is 5, is actually the index of that invisible null character that comes right after it.
So, the fix is incredibly simple, but you have to remember it. To get the last character of any string, you always use its length -1, len -1. This is what accounts for that zero-based indexing and correctly points to the final visible character. So we fixed it. Our len -1 logic is solid. We're good to go, right? Well, what happens when we run into an edge case? This is the second trap, the empty string. And this is where our beautiful solution suddenly and catastrophically fails.
So we've got our len -1 fix, and we're feeling pretty good about it.
But what happens if the input isn't something nice like hello world? What if it's an empty string, just a pair of double quotes? How does our new, fixed code handle that? Okay, let's trace exactly what the computer does. First, strlen of an empty string correctly returns 0, so our len variable becomes 0. Then, our code tries to access the index len-1, which, well, that becomes 0-1. And now the program is trying to access mystring-1. And there it is. Trying to access a negative index is completely illegal memory access. You're basically asking for a piece of memory that doesn't belong to your string, and the operating system is not having it. It steps in and shuts your program down, hard. That's a runtime error, a crash. And that is the answer to our original puzzle.
You know, this whole exercise isn't just about one weird bug. It's really about a bigger idea, a philosophy called defensive programming, which is all about writing code that expects and protects itself against these kinds of tricky edge cases.
And as this expert tip points out, C strings really demand your full attention. The real solution to our crash is defensive programming. Before you even try to access len-1, you first have to check if the string is empty. A simple if len greater than 0 check is the defensive shield that would have prevented this entire problem from the start. It's a constant exercise in thinking, what could go wrong here?
So the real takeaway here is that even the most basic, fundamental building blocks of our code can have some really surprising and dangerous behaviors.
So, today we're going to tackle one of the most fundamental pieces of C programming, the main function. But we're not just going to talk about it, we're about to unlock a hidden power inside of it that's going to completely change how you build and interact with your programs.
I mean, think about it for a second. Most of the C programs we start with are kind of like a closed box, right? They run, they do their one specific thing, and then they're done. But what if? What if you could give that program instructions the moment you start it without ever having to touch the code again? Well, that's the exact problem we're going to solve today.
Okay, so let's get into it. And we're going to start on some familiar ground, the program's entry point.
We all know this one, int main function. It's the front door to every single C program out there. It's clean, it's simple, it's totally reliable. But on its own, it's also a bit isolated. It can't hear anything you might yell at it from the command line when you launch it. It just starts running its pre-written instructions, no questions asked. But what if we could give that front door, a doorbell? Or maybe a mailbox. Let's check out the upgrade and see how everything changes. And here it is. This is the secret sauce. By adding just 2 simple parameters inside those parentheses, int argc in char star argv array, we've just given our main function a massive upgrade. We've given our program the ability to receive instructions directly from the command line. This is the whole key.
So what's the deal with argc and argv? I know they might look a little intimidating at first, but honestly, they're super straightforward. Let's break them down one by one.
First up, we've got argc. Just think of it as the argument count. That's all it is. It's just a simple integer, a number. Its one and only job is to count how many different items or strings you typed on the command line when you ran the program. And here's a little detail to remember. It's always at least 1. And then we have argv, which stands for argument vector. So if argc is the count of the arguments, well, argv is the actual list of arguments. It's an array of strings, basically a container that holds the actual text of every single thing you passed in. So how does this all get organized? Well, argv is just a nice, neat, ordered list. The very first thing at index 0 is always the name of your program. That's why argc is always at least 1, right? Then the first actual instruction you gave it is stored in argv1, the second one in argv2, and it just keeps going like that.
All right, theory's great and all, but let's see this thing in action. We're going to walk through a real-world example so you can see exactly how the command line talks to your code.
Okay, so imagine you've compiled your program, you're in your terminal, and you type this command, .a.out, 1, 2. So you've just given your program its name, plus 2 extra pieces of info. What actually happens inside the machine now? So before your main function even gets a chance to run, the operating system does a little bit of prep work for you. First, it counts everything you typed. It sees ./a.out, that's 1, 1, that's 2, 2, that's 3. So it sets argc to 3. Then it creates that argv array and just slots each of those 3 strings into it. And only then does it hand control over to your program, which now has all this awesome information ready to go. And this table just makes that translation crystal clear. You can see the direct mapping, right? The total count, 3, goes straight into the argc variable. The command you typed, ./a.out, becomes the string in argvv0. The word 1 becomes the string at argvv1, and 2 lands right in argvv2. It's a perfect one-to-one conversion from your command into variables that your code can actually read and use.
So, we've seen how it all works under the hood. But what does this really mean for us? What's the big picture takeaway here? Let's talk about the new power you've just given your program. You know, this all boils down to one absolutely crucial point: flexibility. You can now change how your program behaves without having to rewrite and recompile it every single time. Just think about it. You can tell it what file to open, what number to process, or maybe a setting to turn on or off, all from the outside. This makes your software incredibly dynamic and way more powerful.
And really, that's what this is all about. You've just unlocked a fundamental tool for creating programs that are truly interactive, that are configurable. Ever felt kinda stuck using just the basic data types in C? Like integers and characters? Well, today we're gonna break out of that box. We're unlocking a really powerful idea that lets you go way beyond the basics and start building your own custom data types. So let's just imagine for a second you're building an app. You've got a person's name, their email, their phone number, all these little pieces of information. In your mind, they obviously all belong to one person, but in your code, they're just separate variables floating around. The big question is, how do you get the computer to see the connection? Right. We're about to take a big step up from the simple building blocks we're all used to. We're going to see why those basic types, while super useful, just can't handle the complexity of the real world by themselves.
Look, we all get integers, characters, and floats. They're awesome for counting things or storing single letters. But what about something bigger? How do you represent a whole user profile or a product in your online store? A single int or char just isn't going to cut it, is it?
Okay, to make this totally concrete, let's zoom in on a problem we've all thought about: building a simple digital contact list.
So right now, if we wanted to store a contact, our first instinct would probably be to use what we know. We'd have a character array for the name, another one for the email, maybe an integer for the phone number. But see, that's not how we think about it. To us, it's not three separate things, it's one single contact. There's a huge gap between our logic and what the code is actually doing.
And that is the absolute heart of the problem. The name, email, and phone number are all attributes of one person. They're deeply related. But the code has no idea. It just sees three unrelated variables. And this makes our programs messy, harder to fix when they break, and honestly, they just don't feel right.
Okay, so there's got to be a better way, right? There must be some way to group this stuff together, to teach the computer, hey, these things belong in one package. And you're right, there is. Which brings us to the solution. And that solution is called an abstract data type, or ADT for short. Now, the most important words on this slide are you define yourself. This isn't something C just gives you out of the box. It's a tool that lets you, the programmer, literally invent brand new types of data. Let me put it another way. You're not stuck with just int and char anymore. You are about to be able to create a contact type, or a car type, or a spaceship type. Whatever you need, you get to decide what it's made of. So that all sounds great, but how do we actually do it? How do we make this happen in C? Well, C gives us a special keyword, a specific tool built for exactly this job. And that keyword is struct. This one little word is the key. It's what lets us bundle all those different variables together into one neat logical package. Think of a struct as a blueprint. You're not creating the data itself, not yet. You're just drawing up the plans. You're telling the computer, hey, anytime I create a thing of this new type, it's going to have these specific pieces inside of it. All right, enough talk. Let's get our hands dirty. We're going to take that struct keyword and use it to finally fix our contact list problem the right way. And the cool thing is, the syntax is actually pretty simple. You start with the word struct, you give your new type a name, like contact, then you open up some curly braces, and inside, you just list out all the variables that make up your new type. And here it is, in action. See? We write struct contact. That's our blueprint declaration. Then, inside the braces, we define the members, a character array for the name, another for the email, and an int for the phone number. Oh, and you can't forget that semicolon at the very end. It's super important.
Just like that, we've bundled 3 loose variables into a single, organized contact unit.
Now, this is so much more than just a way to make your code look cleaner. This is a fundamental change in how you can think about and organize data. It leads to code that's easier to read, easier to maintain, and frankly, easier to build on.
And this is where things get really, really cool. You can mix and match. This flexibility is what unlocks the true power of using structs.
A struct can hold anything you want. You can toss in numbers, text, all of the basic types. But here's the game changer. You can put other structs inside of your struct. So for example, your contact could have another struct inside of it called address. You can start building these complex, layered data structures that perfectly match things in the real world.
So, if you take one thing away from this, let it be this. Using structs isn't just a neat trick. It is the absolute foundation for building any program that does anything remotely complex. It's how you organize information, it's how you pass complicated data around, it's how you bring the real world into your code.
And that really just leaves us with one final thought. You're not just a user of data types anymore. Now, you're a creator.
Have you ever wondered how you teach a computer something that we as humans just know? Like what a date is. To us, it's second nature, but to a computer, it's a completely abstract idea. Well, today we're going to pull back the curtain and actually build one right from scratch.
So let's start with a question. If you had to describe a date, say October 10th, 2017, to a machine that only really gets numbers and basic text, how would you even begin? It's not as simple as just typing it out, right? We need to be a lot more specific.
And that's where we need to start. The very first step is to stop thinking of a date as one single thing. Instead, we have to break it down into its smaller, much simpler parts.
See, a computer doesn't look at 10 OCT 2017 and understand it. It sees 3 separate pieces of information. It sees a number for the day, that's an integer. It sees some text for the month, that's a string. And it sees another number for the year. Breaking it down like this is our foundation. It's the key to the whole thing.
Okay, so now we have our ingredients: a day, a month, and a year. But how do we tell the computer that these 3 things belong together? We need a way to bundle them into one neat package. And in the C programming language, we have the perfect tool for that. It's called a struct.
A struct, which is short for structure, is pretty much exactly what it sounds like. It lets us define our own custom data type by grouping a bunch of different variables together. The best way to think about it is like a blueprint. We're not building the house just yet, we're drawing up the plans for what every date is going to look like.
So how do we start? It's simple. We just type struct date, followed by an opening curly brace. This little line of code is us telling the computer, hey, pay attention, I'm about to define a new blueprint, and I'm calling it date.
Now inside those braces, we start adding the parts we identified earlier. First up, int day. This tells our blueprint that every single date we create from now on will have a special spot inside of it to hold a whole number, an integer, and we're going to call that spot day.
All right, next is the month. We add char month 4 to make a little slot for the text. Now, I know what you're thinking. You're looking at that 4 and going, wait a minute, OCT is only 3 letters long. And that is a fantastic observation. It actually points to a really important detail about how C handles text, and I promise we'll get to that in just a second.
And to finish it off, we add int year for the year, and then we close our blueprint with a final curly brace and a semicolon. And that's it. We've done it. Our blueprint is complete. We have officially taught the computer the structure of a date.
Okay, so let's solve that little mystery of why 4. In C, text strings have a hidden rule. They always have to end with a special, invisible character called a null character. It's basically a stop sign that tells the computer, hey, the text ends right here. So for our month, OCT, we need 1 spot for O, 1 for C, 1 for T, and that crucial 4th spot for the invisible stop sign. It's a weird quirk, but it's fundamental to how C works.
So we have the plan, the blueprint is all drawn up, now it's time for the really fun part. Using that blueprint to build an actual real-life date variable that we can use in our code. Let's bring it to life.
And you know what? Creating one is incredibly simple. Just like you'd type int number to create a new integer, you can now type struct date today. That's it. This one line tells the computer, go grab that date blueprint we made and build me a new variable, call it today. And now, today exists, and it has its own empty slots for a day, a month, and a year. So we have our variable, but it's basically an empty container right now. To make it actually useful, we need to fill it up. We need to put our data, the number 10, the text OCT, and the number 2017, into those slots we designed.
So how do we do that? First, we set the day to 10. Then for the month, we have to use a special function called strcpy, which literally means string copy. In C, you can't just use an equal sign for text. And finally, we set the year to 2017. And now, our today variable is complete. It's full of data.
Now, the real key to making all of this work is that little dot you see. The dot is the magic connector. It's the bridge that lets us go from the main today variable to the individual pieces inside it. Anytime you want to get to a specific part, you just write the variable name, a dot, and then the name of the piece you want, like today.day or today.year.
And there you have it. We started with a pretty simple question and ended up designing and building our own custom data type from the ground up. We've actually taught the computer what a date is. And this technique, this idea, is one of the most powerful concepts in programming.
If you're kind of new to programming, I bet you've had this thought. You're learning about variables, everything's starting to click, and then suddenly you hit this piece of syntax that just feels, well, extra. So today, let's dig into why that extra bit is actually one of the most powerful ideas in all of coding. And this is the big question, right? You already know how to make simple variables, and hey, they work just fine. So why add this extra layer of complexity with things like structs or classes? Honestly, at first glance, it feels like you're just making more work for yourself. But as we're about to see, that little bit of extra work up front saves you from a world of headaches down the road. All right, let's make this real with a simple example. Let's say we need our program to handle a date. What's the most straightforward, most obvious way to do that? Well, you'd probably think a date has 3 parts, right? A day, a month, and a year. So let's just create 3 separate variables. We'll make an integer for the day, maybe a little character array for the month's name, like JAN, and another integer for the year. Seems totally logical, it's simple, and it works. And let's be super clear here. If your program only, and I mean only, ever needs to deal with one single date, this approach is perfectly fine. There's absolutely nothing wrong with it. It gets the job done. But let's be real. Programming is rarely ever that simple, is it? Because this is where that simple, obvious approach starts to fall apart. The moment you need to scale up, even just a tiny bit, things can get messy, and I mean they get messy fast. So let's imagine a really common scenario. Your program doesn't just need a date. It needs to keep track of today's date, tomorrow's date, and yesterday's date. What happens to our nice, simple little system now? Well, boom, all of a sudden, our clean 3-variable setup just explodes into 9 separate variables. Now you've got to come up with unique names for every single piece of data. Today_day, tomorrow_day, yesterday_day. I mean, just look at it. It's already a cluttered mess, and we're only trying to manage 3 dates. And, this isn't just about your code looking ugly. This creates genuine, real-world problems for you as the programmer. The code becomes a pain to read because your brain has to constantly connect today_day with today_month and today_year. It's hard to maintain, and maybe worst of all, it's so easy to make a silly mistake, like accidentally using tomorrow day when you meant to use today day. So there has to be a better way, right? How do we fix this mess? Well, we need a way to tell our program that these 3 different pieces of info, the day, the month, and the year, actually belong together. They represent one single idea. And this is where the really elegant solution comes into play. We use something called an abstract data type, or ADT. Now, don't let that fancy name scare you. All it really means is that we get to create our own custom variable type. It's kind of like a container that we design ourselves to hold all that related information together in one single, neat, logical package. And here's what that looks like in a language like C, using what's called a struct. What we're doing here is basically creating a blueprint. We are defining a brand new custom type of thing called a date. And we're telling the computer, hey, from now on, every single date that we create is going to have an integer for its day, a spot for its month, and an integer for its year, all bundled together. And this right here is the aha moment. This shows you the payoff. On the left, you've got that 9-variable disaster we had before. But look at the right. It's the new way. Just 3 simple variables, today, tomorrow, and yesterday. And each one is of our new custom type.
date. I mean, it is so much cleaner, it's more intuitive, and it just instantly makes sense. Okay, so we've gone from messy to clean, but this isn't just about making your code look pretty on the screen. This fundamentally changes how you work and how you think, and that leads to some absolutely huge payoffs. So let's just break down these advantages. First, your code is undeniably easier to read. Seeing today.day is way clearer than today's score under day. Second, it's just plain easier to develop. When you need to pass a date to a function, you just pass one thing, the date variable, not 3 separate pieces. And finally, trust me, it is so much easier to maintain and update your code in the future.
And hey, don't just take my word for it. The source material for this whole explainer says it perfectly. Using an ADT isn't just some stylistic preference. It's a practical decision that directly makes your code easier to read, and because of that, easier to develop and maintain. It's really a cornerstone of professional programming. So if there is one thing you take away from this, let it be this. When you create an abstract data type, like our date struct, you're doing so much more than just organizing syntax. You are actually organizing your thinking. You're teaching the computer about the real-world concepts in your problem, that a date is a single cohesive thing, and that makes your code a much more powerful and accurate model of reality.
All right, today we're going to talk about one of the most powerful ideas in all of programming. We're going to look at how to take code that's messy, repetitive, and kind of complicated and turn it into something clean, smart, and honestly, a whole lot easier to work with. Let's dive in.
You've been there, right? If you've written any code at all, you've had that moment. You're typing out the same lines for the 3rd, 4th, maybe 5th time, and you're just thinking, there has to be a better way to do this. Well, you're in luck because there is, and it's called a function.
To really see what I mean, let's use a super common example. Just trying to work with dates. You think it's simple, but as you're about to see, the complexity can really sneak up on you and fast.
So say we want a variable for today's date and another for tomorrow's. Look at this. We have to manually set the day, then we have to copy the month string, then we set the year, and then we have to do it all over again for the second date. That's 6 lines of code just to do pretty much the same thing twice. Yeah, it works, but it's clunky and it's just begging for a typo.
Okay, so let's fix this mess. We're going to build what I like to call a date factory. The idea is, instead of building every single date by hand, piece by piece, we're going to have a little machine that just churns them out for us.
And wow, look at the difference. It is night and day. On the left, with the old way, you kind of have to read every single line to figure out what's going on. But on the right, you know exactly what's happening in a single glance. And this isn't just about typing less. It's about making your code speak for itself. It's about clarity. So what is this factory? Well, it's a function that we've called newDate. And you can think of it just like a real factory. You give it the raw materials, a number for the day, a string for the month, a number for the year, and it hands you back a perfectly assembled, ready-to-use date.
And there's no dark magic happening inside our little factory. The function is literally just doing the exact same repetitive steps we were doing by hand before. It makes a blank date, it fills in the parts one by one, and then it returns the finished product. The whole key is that all that tedious work is now bundled up neatly in one reusable spot.
So creating dates is way easier now. That's a huge win. But the real power, the really cool stuff, happens when we start adding a bit of intelligence into our functions. See, we can design functions that actually understand the rules of being a date. They're not just for setting things up. They can perform really meaningful operations for us.
For example, check out this nextYear function. The logic is super simple. It takes in a date, makes a copy of it, adds one to the year, and then returns that new date. It's a small, focused little tool that does one job and does it perfectly.
Okay, that was a pretty simple example, but now we get to the real heart of the matter. Let's see how functions help us manage some truly complicated logic. This is where the real magic happens.
Now, think about this for a second. Figuring out the next day isn't as simple as just adding 1 to the day number. I mean, what happens on January 31st? Or what about February 28th, especially on a leap year? Or December 31st? The logic gets messy, and it gets messy really, really fast.
So we create a function called nextDay, but notice what we're showing here. We don't even need to see the code inside it. We're going to treat it like a black box. We know what it's supposed to do. It takes a date and gives us the next one, but we don't have to care how it pulls it off.
And this right here is the whole point. This is the magic of abstraction.
All of that messy, complicated logic for handling month ends and leap years and all that, it's hidden away, it's contained inside our function so it doesn't clutter up the main part of our program.
The result is code that almost reads like plain English. D equals next day of D. It's so clear. We're just saying, take our date D and update it to be the next day. The complexity is gone and it's been replaced by pure, simple clarity.
And does our little black box actually work? You bet it does. If we give it December 31st, 2017, it correctly handles both the end of the month and the end of the year, giving us back January 1st, 2018. All that complicated logic just perfectly executed behind the scenes.
So look, hiding complexity inside functions like this isn't just a neat little trick. It fundamentally changes how you write and think about your code. It gives us two enormous advantages.
And these are the two golden tickets. First, readability. We've already seen how our main code becomes incredibly simple to follow. And second, and this one is arguably even more important, maintainability. This is the one that's going to save you from huge headaches down the road.
Just imagine for a second that you wrote all this date logic, but you completely forgot about leap years. Hey, it happens to the best of us. The old way, without our function, you'd have to go on this painful hunt through all of your code, finding every single place you calculated the next day and fixing each one. It's a total nightmare that wastes time and probably introduces new bugs. But with our new way, you go to one single place, the next day function, and you fix the logic right there. One change, and your entire program is instantly corrected. That's not just cleaner code, that's building software that's faster to develop and way more reliable. It's a complete game changer.
So that's really the power of taming complexity. You take what's messy, you package it up, and you create these simple, powerful tools for yourself.
Hey, we're going to get into a really common situation you'll run into when you're coding. How do you deal with complex, layered data? Let's dive right in.
All right, so here's the big question we're going to tackle. How do we actually model data that lives inside of other data? Think about it for a second. Your own contact information, right? It's not just one big flat thing. Your address is made up of a street, a city, a zip code. It's nested information. Okay, let's think about it like this, with a metaphor. Imagine a person is a big filing cabinet. Now, inside that cabinet, there's a folder, and it's labeled date of birth. And then inside that folder, you've got a little piece of paper with a year written on it. See the layers? We need a way to build that same structure in our code. So your basic variables, a single number or a piece of text, they just aren't going to cut it for this kind of thing. We need a tool that's built specifically for this kind of organized, layered information. And that's where the nested struct comes in. The official definition is pretty simple. It's just a struct that you use as an element or a field inside of another struct. This is how we solve our problem. This is how we put that folder right inside the filing cabinet.
And check this out, the code looks exactly like our filing cabinet metaphor. You can literally see the date of birth struct, that's our folder, defined right inside the personal info struct, which is our cabinet. It's a perfect one-to-one visual of what we're trying to do.
Right, so we've got our cabinet, we've got the folder inside, awesome. But how do we actually get anything out of it when we need it? It's not enough just to store the data, we have to be able to access it.
Yeah, this is the real practical question, isn't it? How do we reach into that person cabinet, grab the date of birth folder, and then pull out the year from the paper inside?
Well, it turns out you've got two main ways to go about this. There's the direct way, the sort of hands-on approach, and then there's what pretty much everyone agrees is a cleaner, safer, and just all-around better way. Let's look at both.
Okay, let's start with method number 1, the direct approach. This is all about using a little piece of syntax called the dot operator.
Seriously, think of this like you're writing down manual instructions for yourself. You start with the main filing cabinet, info, then use a dot, which basically means go inside to get to the DOB folder. Then you use another dot to say, and now get me the year file. So info.dob.year. It's a path that leads you right to the data. And here it is in action. See that line? We're reaching right into that nested structure to set the year. It's fast, it's direct, it totally works. But, and this is a big but, it comes with some real drawbacks.
Which brings us to a much better way to handle this, using functions.
Instead of digging through that cabinet yourself, what if you had a helpful assistant? You wouldn't need to know where the folder is, right? You just say, hey,
get me the year of birth. That's exactly what a function does for you here. It's a middleman that handles all the messy details for you. And this is how we build that assistant. We create this function, getDobYear. Its whole job in life is to take in the person's info, do the digging for us, and hand back just the year. It's like a specialized messenger for one specific piece of data. So let's put these two side by side, because this is where it all clicks. With direct access, you are literally hard-coding the path, info, then dob, then year. If later on someone decides to rename dob to, say, date of birth, boom. Every single piece of your code that used that direct path is now broken. With the function, you just keep calling your assistant getDobYear. If the structure changes, you only have to update that one single function. The rest of your program doesn't have a clue anything even changed.
Okay, so why are we obsessing over this? Why does this distinction really matter when you're out there writing real code? Well, it's all about writing code that can last, and that's easy for you and others to work with down the line.
Using functions is like a trifecta of wins. First, organization. All the logic for how to get a piece of data lives in one single spot. Second, maintainability. Like we just saw, it's so much easier to update. And finally, safety. It creates a protective barrier, which can help prevent other parts of your code from accidentally changing data they have no business touching. And it all boils down to this one crucial point. By using a function, you hide the messy implementation details from the rest of your program. This is a huge concept in programming called abstraction, and honestly, it is an absolute game changer for writing good software. You create these simple gateways, like our getDobYear function, that hide all the complexity underneath.
And that's really the big idea I want to leave you with. This whole concept of abstraction, of hiding the details behind a simple front. It's not just for nested structs. It is everywhere in good code. So as you go forward, ask yourself, where else in my own projects can I use this principle to make what I build stronger, cleaner, and just better?
All right, welcome. Today we're going to peel back the curtain on a really fundamental piece of code, something you almost definitely use every single day, probably without even thinking about it. So yeah, let's dive right in. I mean, think about it, right? You're typing away, you delete a word, and then whoops, you hit Control-Z and boom, it's back. How in the world does your computer remember the very last thing you did?
Well, that's the secret sauce right there. It all comes down to a simple but incredibly powerful idea called a stack. And today, we're going to build one from the ground up using the C programming language.
And we've got a super clear game plan. First, we'll get the big idea of what a stack even is. Then, we'll look at the code blueprint. We'll see how to get it started, watch it in action, and then wrap it all up with the main takeaways. Easy enough, right?
Okay, first up, section 1. So, what is a stack? Before we even think about code, let's just get our heads around the concept itself. So here's the absolute key concept. Last in, first out. You'll hear this called LIFO all the time. The best way to picture it? Think of a stack of plates at a cafeteria. When a clean plate comes out, you put it on top. In programming, we call that a push. Now, when you need a plate, you can't just pull one from the middle, can you? No way. You have to take the one on top, the last one you put there. We call that a pop. The last plate in is the first plate out. That's the entire idea in a nutshell. Which brings us to section 2. Now that we've got the idea, how do we actually explain that to a computer? We need a blueprint.
And here it is. This is our blueprint in C. It's called a struct. And you can think of a struct as just a custom container you design yourself. It's a way to bundle a bunch of related things together into one tidy package. And this struct, which we've named stack, has everything we need to make our stack work.
So let's meet the team inside our blueprint. First, you've got head. Think of head as the manager. Its job is to always know where the very top of the stack is. Then there's max size. That's kind of like the bouncer. It sets the rules for how many items can even get in. And finally, you have LIFO 10. This is the actual container, the shelf, where we're going to store our 10 items.
On to section 3. Okay, so we've designed the stack, but before we can use it, we have to set it up. It's like hitting the reset button on a game before you start playing. You need a fresh, clean start. And this little function right here, initialize, does exactly that. It's a one-time setup that gets our stack ready for business.
So what's actually happening here? Well, it sets our s.head to 0. And this is super important. Ahead of 0 is our signal that the stack is totally empty. It also sets s.maxSize to 10, just confirming the capacity we decided on. And just like that, we are ready to roll.
Okay, section 4. Now for the fun part. This is where we actually make the stack do stuff. You know, a stack really has two main jobs: putting things on the stack, which we call push, and taking things off, which we call pop. We're about to give our stack these superpowers.
But hang on. Before we do anything, we need a way to check on our stack. You know, hey stack, you got anything in you? This is a really critical safety check. You definitely don't want to try and pop an item that isn't there. That would crash your program. So we need a reliable way to ask if it's empty.
And the code for this is just beautiful in its simplicity. This isEmpty function just asks one simple question. Is our head manager pointing at position 0? If it is, well, then we know for sure the stack is empty. Now, this works because of a cool little feature in C. That double equal sign, it's not just asking, are these equal? It's actually returning an answer. It gives you back a 1, which means true if s.head is 0, or is 0 for false if it's anything else. It's a super efficient way to get a quick yes or no.
All right, let's get to that first core action we talked about, putting stuff onto our stack. This is the push operation. This is the last in part of LIFO.
And here it is. This is the push function. This little block of code is the engine that takes a piece of data and places it right on top of our stack.
So let's walk through this step by step. First, a safety check. Is there any room left? Is our head counter still smaller than our max size? If it is, great, we proceed. Step 2, we drop our new data into the container, right at the spot the head is pointing to. And then, the crucial final step, we move the head up by 1. Now it's pointing at the new top, ready for the next push. And that's it. The pop operation, by the way, would do the exact reverse. Move the head back down, and then grab whatever's there. That's how you get that last in item to be the first out.
And that brings us to our final section. Let's just pull back for the big picture. What did we actually just put together here?
So if you remember anything from this, remember these key points. A stack is all about that last in, first out idea. And it's what makes things like the undo button possible. In C, we use a struct as a blueprint to hold all its parts. The head variable is the absolute MVP. It's our guide to the top. And the push function is how we add new stuff by putting it at the head and then bumping the head up one spot.
And that leaves us with a really interesting loose end, doesn't it? Our push function is smart enough to check for space, but if the stack is full, it doesn't do anything. The data just gets ignored, it disappears. So what should happen? Should the program show an error? Should it throw out the oldest piece of data to make room? That's the kind of question you have to answer to build a truly solid professional-grade stack, and it's a perfect thing to think about.
Have you ever wondered how your browser's back button actually knows where to go? Or how a program can undo your last 20 actions in perfect order? Well, the secret often lies in one of the most fundamental ideas in computer science, the stack. So today, we're going to dive in and break down exactly how it all works. Okay, so the easiest way to get your head around a stack is to just picture a pile of plates at a buffet, right? You can only add a clean plate to the top of the pile, and you can only take a plate from the top. You can't just slide one out from the middle of the stack. The whole thing would fall over. And that one simple rule, that's everything. And that simple rule gives us the absolute golden rule for every single stack. Last in, first out. Or, as you'll always hear it, LIFO. The very last plate you put on the pile is always the first one you're going to take off. If you walk away with just one thing today, make it LIFO. It's the whole game. So that's the idea. But how do we get a computer to understand a pile of plates? Well, it all boils down to a few core commands, or functions, that lay out the roles of the game for managing a stack. First up, empty as empty. It's exactly what it sounds like. It's a quick check to see if we have any plates in our pile at all. Then we have push. That's our command to add a new item or a new plate to the top. Pop is the exact opposite. It takes that top item right off the stack. And then there's this handy one called peek. What if you just want to see what's on the top plate without actually taking it? That's peek. It's a little sneak peek. All right, enough theory. Let's actually see this thing in action. We're going to build up a small stack piece by piece, and then we'll tear it back down so you can see exactly how these functions play together. First things first, we got to create our stack. You can think of this as just setting aside an empty space, ready to hold our stuff. For our little demo, we'll make one that has room for 5 items. Right now, it's totally empty. Okay, let's add our first item. We use the push command to put the number 4 into our stack. Since it's the very first thing we've added, it goes right to the bottom. It's the foundation of our pile. Next up, let's push the number 10. And where does it go? Well, following our rule, it gets placed right on top of the 4. Now, 10 is the new top of our stack. And let's do one more. We push the number 3. It lands right on top of the 10. So if you look at our stack from the bottom up, we have 4, then 10, and now 3 is sitting right at the very top. Now, what happens when we pop? This is where that LIFO rule kicks in. Last in, first out. The last number we put in was 3, right? So it's the first one to come out. The pop function grabs the 3, removes it, and just like that, the new top of the stack is now 10. Simple as that. Okay, so this all makes sense, right? Pushing, popping, it's an elegant idea. But it kind of begs the question, doesn't it? How does a computer, a machine that just thinks in memory addresses, how does it actually build this pile of plates? Let's lift the hood and take a look. You might be surprised to find out that one of the most common ways to build a stack is with another data structure you probably already know, a simple array. Its straight, linear layout is actually the perfect tool for the job. So, here's the trick. We take a plain old array, but to make it act like a stack, we need a way to keep track of where the top is. And for that, we just use a tiny variable, which we'll call head. Think of head as a bookmark or a pointer. When the stack is totally empty, head just points right at the very beginning at index 0. So when we push 4, 2 things happen. First, the computer sticks the number 4 into the array right where head is pointing, at index 0. Then, and this is the crucial part, it moves the head forward by 1. So now head is at 1, pointing at the next open spot, ready for whatever comes next. See the pattern? Let's do it again. We push 10. The 10 goes into the slot head is pointing at, which is index 1. And just like before, the head scoots over one more spot. Now it's pointing at index 2. And one last time, we push 3, it slots into the array at index 2, and the head moves on up to 3. That head variable is always staying one step ahead, always pointing to the next available spot on top of our stack. So what about pop? This is where it gets really clever and super efficient. You'd think we'd have to actually delete the data from the array, but we don't. To pop an item, all we do is move the pointer back. We just decrease the head variable by 1. By moving head from 3 back to 2, the number 3 is now effectively gone. I mean, sure, the value is technically still sitting in memory, but as far as the stack is concerned, it's out of bounds. The next time we push, it'll just get overwritten. It's so simple and incredibly fast. So, we've gone from a pile of plates all the way down to how arrays and pointers work. Let's take a step back and boil it all down to the key things you really need to remember. First, the core concept. Just think pile of plates. It keeps things simple. The one rule to rule them all, last in, first out, LIFO. The main actions you'll be doing are push to add to the top and pop to remove from the top. And behind it all, you can build the whole thing using just a simple array and that little head variable to keep track of everything. So now you get it. You understand the power of last in, first out. And here's the really cool part. Once you know this rule, you start seeing it absolutely everywhere. The undo button you use all the time, that's just a stack of all your recent actions. Your web browser's back button, that's a stack of the pages you visited. In the world of computer science, you've got these 2 little words, pop and peek, that can cause a whole lot of confusion. They both let you look at the top of a data stack, right? But here's the thing. One of them changes everything, while the other is totally invisible. Today, we're going to finally clear that up and uncover that one critical difference. So let's start with a really common problem in programming. Picture this. You're building an undo button for an app, or maybe a browser's history feature. You always need to get the very last thing that just happened. So how do you build that so it's lightning fast every single time? Well, that's the exact problem that the data structure known as a stack was created to solve. And the solution is this beautifully simple thing called a stack. Honestly, the easiest way to get it is to just picture a stack of plates in a cafeteria. You can only take the top plate, and when you add a new one, it goes right on top. This super simple but powerful idea has a name, last in, first out, or LIFO for short. So what does LIFO actually mean when you're coding? Well, it's a strict rule. The last item you put on the stack is the only one you're allowed to touch. Seriously, no reaching into the middle, no grabbing from the bottom. You always have to work from the top. And that strict rule, that's actually its superpower. It's what makes a stack so incredibly fast and efficient. Okay, so how do we actually get that top item? The main tool for that job is the pop function. From now on, whenever you hear pop, I want you to think get and remove. It's the action of literally taking that top plate off the stack. Let's walk through what the computer actually does when you call pop. First, a quick sanity check. Is the stack even empty? Because you can't take something that isn't there, right? If we're good, We then store the value from the top item. Just make a copy so we don't lose it. Then, and this is the most important part, we move the head pointer down by 1. This is the moment that item is officially removed. And finally, we return that value we copied, handing it back to whatever part of the program was asking for it.
But here's the big secret about POP that a lot of people miss. It doesn't actually delete anything. That would be slow. Instead, it just moves that head pointer. The old data is still just sitting there in memory, but the stack doesn't know about it anymore. It's kind of like ripping a page out of a book's table of contents. The chapter is still there, but as far as the book is concerned, it's gone.
Okay, so that brings up a really good question. What if you just want to look at what's on top, without actually removing it? I mean, there's got to be a better way than popping it off just to have to push it right back on again. And of course there is. For that exact situation, we have the peek function. And just like the name says, peek is all about taking a quick, non-destructive look at that top item. You get the information you need, but you don't change the stack at all. And here's the best part. If you get how POP works, you pretty much already understand peek. Their code is almost identical. They both look at the top item, but they're separated by one tiny yet absolutely critical difference. All right, let's put them side by side. The final showdown, POP versus peek. It all comes down to a single operation that decides whether the stack is changed forever or not at all. And this chart makes it crystal clear. Check it out. Their action? Totally identical. Both of them grab the value of the top item. But the effect? That's where everything changes. POP moves that head pointer down. It's a destructive action that makes the stack smaller. Peek, on the other hand, leaves that pointer right where it is. It's just a passive observer. So the whole thing, the entire difference, just boils down to whether or not you move that head pointer. To move or not to move. That is the question that separates these two. One action changes the state of your data, and the other simply looks at it. So let's boil this all down. POP reads the top item and then removes it by moving that head pointer. Peek, however, only reads that same item and leaves everything exactly as it was. That's it. That one little decision, to run that line of code that moves the pointer or not, is the only thing that separates them. And just as a little safety tip, if you do try to pop from an empty stack, most systems will return an error or a special value like -1 to let you know something's wrong. So I'll leave you with this question to think about. Now that you know the difference, when might you need to know what's coming next without actually changing the order of things? Think about it. Maybe you're validating what a user is about to do, or you're checking the state of a game before making a move. That right there is the strategic power of the peek. So when we're working with data, we usually reach for things like lists or arrays, right? But what if there was a more intuitive, more human way to organize our information? Well, today we're going to dive into a really powerful data structure that does just that, the dictionary. And trust me, it might totally change how you think about storing data. Okay, so to really get why dictionaries are such a big deal, we first have to talk about the limits of what most of us are used to, and that's arrays. With an array, everything has a numerical spot, an index. You want the first thing, you got to ask for index 0. The 10th thing, index 9. And look, that system works sometimes, but it's definitely not perfect for everything. All right, I want you to picture something for a second. You've got this giant, heavy Oxford English dictionary in front of you, and I ask you to find the definition of aardvark. But here's the catch. You can't look it up alphabetically. You have to know the exact entry number. I mean, that sounds completely ridiculous, doesn't it? You'd be lost. You'd have absolutely no clue where to even start looking. And that right there, that just nails the problem. Trying to think of aardvark as, item 27, it's just not convenient. It doesn't click for us humans. It feels clunky and unnatural. There's got to be a better way, right? Well, you guessed it, of course there is. And that's what brings us right to the main idea behind a dictionary, getting away from those rigid numbers and using a much more natural way to find our data. And here is the absolute game changer. So instead of telling the computer, hey, give me item number 27, what if we could just say, hey, tell me about aardvark? What if the thing we're looking for is the way we find it? That simple shift in thinking is what makes dictionaries so powerful. And you can see the difference so clearly right here. Over on the left, with an array, we've just got this position, 27. It doesn't mean anything on its own. But then, look at the right. The dictionary uses a meaningful key. The key, aardvark, tells you exactly what you're looking for. It just makes sense. It's how our brains are wired to work. So how does this actually work? Well, a dictionary is built on two super important parts. They're called the key and the value. So let's break that down, and we'll stick with our real-world dictionary analogy. Okay, first up, we have the key. Think of the key as your search term. It's the unique thing you use to find the info you're after. So in our running example, the word aardvark, that's our key. It's the piece of the puzzle you already have. And once you have the key, well, that's how you find the value. The value is the good stuff. It's the actual data you were looking for all along. So if aardvark is the key, then the definition, an African mammal, that's the value. Simple as that. The key unlocks the value. Now here's the really important part. A key and its value are always locked together. They're a package deal, a pair. You can't have a key with no value, or a value just floating around without a key. So this whole thing, aardvark, African mammal, that's one complete entry in our dictionary. So this idea of pairing things up, it's a really powerful concept. And we can actually take this idea beyond just pairs of two, which leads us to this related concept called a tuple. So what is a tuple? Well, at its core, it's just a collection of values in a specific order. Think about it like contact info, right? You might have your name, your phone number, and your email, all grouped together. That's a tuple. So our key value pair, that's just a 2-item tuple. But you can have 3-item tuples, 4-item tuples, really as many as you need to bundle your information. But what makes tuples really, really useful is how flexible they are. Check this out. Like we said, our aardvark African mammal pair is a simple 2-item tuple. But now look at this next one, 7 ABC 5.0. You see that? We have a number, then some text, then a decimal number, all living together in the same collection. That is a huge deal. You usually can't mix and match data types like that in a normal array, and that's what makes tuples so powerful and versatile. All right, so let's tie this all together. The main thing to remember here is that dictionaries with their key value pairs give us a way to organize data that just feels human. It makes sense to our brains. We're not looking up some random number. We're looking up something by a name that actually means something to us. It's totally intuitive. Okay, so I want to leave you with one final thought to chew on. Think about the contacts list on your phone. When you want to call your friend, do you think, I think they're contact number 27? Of course not, right? You type in their name. So based on everything we've talked about, is your phone's contact list really an array, or is it a dictionary?
Have you ever stopped to think about how your phone's contacts list works? Or how a website can just instantly pull up your user profile? Well, it all boils down to a super fundamental data structure, and today we're actually going to build one from the ground up in C. It's called a dictionary, and trust me, it's the engine behind so much of the tech we use every single day. Seeing how it's made is the best way to really, really get it.
So to get us started, let's frame this whole thing with a pretty fun challenge. You ever wanted to make your own secret code, cipher, to send messages that no one else can read? Well, the dictionary we're about to build isn't just some abstract programming exercise. It's going to be the key to your very own secret decoder.
You see, the heart of any simple cipher is just a mapping system. All we need is a way to say, okay, the letter A is now the number 1, and B is going to be 2, and you get the idea. That's exactly what a dictionary does. It just links one piece of data, which we call a key, to another piece of data, the value. Simple as that.
Okay, so before we can write a single line of code to store our secrets, we have to do what any good architect does. We need a blueprint. We have to design the containers that are actually going to hold all our data. We'll start with the tiniest piece and then build a bigger structure that holds them all.
So here it is, our smallest building block. It's a structure, and we're calling it a key-value pair. And just like the name says, it holds two things, a character, which is our key, and an integer, our value. The best way to think about it is like a single entry in your phone's contact list, a name paired with a number.
All right, now let's zoom out to the main container. The dictionary structure is basically our whole filing cabinet. It's got an array inside that can hold up to 1,000 of our key value pair entries. And yeah, for now, that's a fixed limit. That's a design choice we might come back to. And really important, it also has a little counter called size that just keeps track of how many entries we've actually put in there so far.
So, we've got the blueprint. But how do we get our secret codes into this dictionary? For that, we need an action, right? A function. We're going to call it put. And its entire job is to take a key and a value and just place them inside our new structure.
So how does this put function actually work? Well, it's a simple 5-step process. First, it gets the key and the value you want to store. Second, it just peeks at the dictionary's current size to find the next empty slot. Easy enough.
Third, it bundles that data up into a new key-value pair. Fourth, it plops that new pair right into the array. And finally, and this is super important, it bumps the size up by 1 so we know where the next entry should go.
Storing data is only half the battle, right? Now we need a way to look up a character and find its secret number. This is the decode part of our whole plan, and for that, we're going to use a function called get.
The get function is kind of like a little detective. It starts at the very beginning of our array at index 0. It looks at the key in that first slot and asks, hey, are you the key I'm looking for? If the answer is yes, boom, it returns the value and its job is done. If not, no big deal. It just moves on to the next one and asks again, and again, and again, all the way down the line.
Now what's really cool is that this detective work, this one-by-one check, actually has a name. It's called a linear search. It's pretty much the most straightforward way you can find something. You just check every single item until you find your match. It's simple, it's reliable. But what's the catch? Well, imagine our dictionary had 1 million entries. This method could get really slow, really fast. And that's a classic trade-off in computer science, simplicity versus efficiency.
All right, so our decoder works, but a huge part of being an engineer is looking at what you just built and asking, okay, how could this go wrong? Where are the weak spots? And believe me, our simple little design has a couple of pretty big cracks in its foundation.
And this gets right to the heart of the problem. If we mess up and add the letter A to our dictionary twice, maybe with 2 different numbers, well, our get function is always going to stop at the first one it finds. It'll completely ignore any others. So we're getting an incomplete and maybe even a totally wrong picture.
And the real root of this problem? It's our put function. See, it blindly adds a new entry every single time without ever checking if that key is already in there. A smarter, more robust dictionary would first search for the key. If it finds it, it would just update the value that's already there instead of making a messy duplicate.
So let's just boil it all down. Our dictionary has a major flaw. It doesn't know how to update existing keys. And that leads to these duplicate entries and completely unpredictable results from our get function. Now, this isn't just some tiny bug. It really undermines the reliability of our entire data structure.
And that brings us to the final, and I think most important thought. We've built the machine. We've found the cracks in the code. So now the challenge is officially passed to you. Thinking about the logic of our put and get functions, how would you rewrite them to handle these updates properly and make our simple dictionary truly awesome?